Hey guys, welcome to another problem of the day series of GFG and LeetCode problem of the day. So proceeding to our LeetCode problem, the problem was length of the longest subarray with at most k frequency. And our problem statement is you are given an integer array nums and integer k. The frequency of an element x is the number of time it occurs in an array. An array is called a good if the frequency of each element in this array is less than or equal to k. Now we have to return the length of the longest good subarray of nums. So the condition is an array is called or a subarray is called good if the frequency of each element in this array or the subarray is less than or equal to k. So for each element in the subarray, the frequency of this element should be lesser than k. And now in the given example, it is said that length, the longest possible good subarray is 123, 123. Because as you can see that this one is considered 123 123 because in this subarray first thing it is the longest, second thing each element frequency is less than or equal to 2, this one and this one makes up to frequency 2 and its frequency is less than or equal to 2. Now the possible answer could be 231 and 231, this one 231 and 231, but as we have already encountered a subarray with length 6, then it's fine if we just don't consider that. In the second example of k is 1, and as you can see the longest subarray that we could form is of 1 and 2 in this case, or 2 or 1 or 1 2 and etc etc. So our constraint are between nums dot length is 1 and 10 is to 5, and our the element in our nums are between 1 and 10 is to 9, and our k is between 1 and nums dot length. Okay, so proceed to the explanation. So what could a brute force approach will be? So the one of a brute force approach will be to start from I equal to 0 to n, and then we will have an inner for loop which is from j equal to I to n. Now, at each position, we will find out the number of elements or the longest subarray that we could form with equal number of elements. Now, to find out the equal number of elements, what we could do, we could use a hash set. So the problem, our brute force approach is something like that for I equal to 0 to n, then j equal to 0 to n, and then we will have a hash set to check that if our subarray doesn't exceed our k. So it might be nums. So we will add a nums of j, and then if we check if our s dot size is greater than k, then we will just update our result to max of result comma uh, till max of result comma the, as you can see, the s dot size, which is our, no, and not the s dot size. We will use our formula j minus I plus 1 to check out the number of elements or to check out our window size, and then we will break out of this loop. Now this will check for every uh, position of I, and will check if what is the longest subarray that we could form using our current window. So this is a brute force approach. So as you can see that it won't fit in our constraint, it will definitely give a time limit exceeded error. So what we could do is, as you can see in this subarray, uh, in this following code, what we are doing, we are considering each element or each index, and from the each index we are finding out the longest subarray. So why not just do something like that? If we found out our maximum length subarray, then we definitely know that there is certain element which is making our length of the subarray greater than k. So why not just remove some element from the start? So first thing, it will make sure that we our window size is lesser than or equal to k, and or, and the second thing, it will make sure that it fits in our constraint. So it will also remove this inner J loop. So what we will do is, if we at certain point, if we find out our length of that subarray is greater than or equal to k, that means we have to remove some element from the start. So so in this approach, there are two methods we will use. The first method will be of sliding window approachness. Second, and then we will use a data structure hash map to store or to find out the number of elements in that subarray. So removing this and proceeding to our explanation. So what we will do in we will have a hash map that will store all the element and its frequency. So our I currently is at zero. So at zero we have one. So one equal to and its frequency one. Now I updated it to two and our two will become one. Now our three will be updated to now I will be updated and our I is two and at I two we have three. So three is updated to one. Now we have encountered another number one, and now our I is three. So as our I is three, we have a one there. So as it is, so we will update in our hash map. Sorry, so we will update in our hash map, and then in this we have find out that it is not making any effect to our size. Our size still remains three. The frequency of each element still remains. The frequency of each element still remains two. And now our I will be incremented to 4 and our 2 will be updated. Now our I will be incremented to 3 and sorry now increment to 5 and our will be updated and this will be updated to. Now I will be incremented to 6. Now we are seeing that there is a certain element 2 which which is also present in our hash map and which has a frequency 2 lesser than equal to 2. So in this case, what we will do is now we may have to make sure that we have to remove some element or we have to encounter an element from start of a window. We have to encounter a two. So to make sure that the frequency remains to itself. So we don't remove. So we won't remove the frequency of our element in our from our hash map. We will just remove it from our window. So our J is 0. So as our J is 0, it will be is it a 0? So we is it 2? No, it is not 2. So we will decrement our value from our hash map to 1 and our J will be 1. Now we have a 2 here. We have encountered a 2. So as we have encountered a 2 here, we just have to make sure that we increment our J to 2. So we are making sure that our window remains from 2 to 6 and we are making sure that any of its element frequency is not being greater than k. So we will to and the next thing to update our result, what we will do is we will do a j minus I plus 1. This same j minus I plus 1 will give us the size of the window that we are currently holding to as our sorry not j, it is I minus j plus 1. So as I minus j plus 1 is, so 6 minus 2 is 4 plus 1 is 5. So from 2 to 6, there are total number 1, 2, 3, there are total 5 elements, and this will be our answer. But at start, from as you can see from the 0 to 5, we have already encountered 6, so its result won't get updated. Now our I will be incremented to 7. Now we have a 2 here again. And there is a 2 present in with our sum. So what we will do in this case is we have to increment our j and and to make sure that we have all the elements frequency less than or equal to 2. So our j will be incremented to 3 and so our j is at 2. So we have to remove first this element from our hash map. So it will decrement it to 1 and j will increment to 3. At 3 we have 1. 1 will be get to 0. Now at now our increment j will be incremented to 4. Now we have encountered a 2 and our so in this case we would decrement the frequency from our hash map, we will just increment our j to 5. So now we have each element frequency less than or equal to k. And our window size will be between 5 and 7. Now what we will do, we will have increment our I to 8. So as we incremented I to, we incremented it in our hash map also. So it will be 2. As 3 is not is 3 frequency less than or equal to k, we will just update our result with I minus j plus 1. So as the window size is just 4, our result will be still same, which is 6. So in this way we could achieve this. So in this way we could achieve our result and the solution to this problem. So moving forward to the GFG problem of the day. So the problem is city with the smallest number of neighbor at a threshold distance. Now it's really a good problem for the ones who are solving graphs problem and graph problem and know and should know some concept of Dijkstra's algorithm and some graph algorithm. So there are n cities labeled from 0 to n minus 1 with m edges connecting them. We are given an array edges where edges of I equal to from I to I and weight I. They represent a bidirectional and weighted edge between city from I to I and given the integer distance threshold. Now you need to find out a city with the smallest number of cities that are reachable through some path and whose distance is at most threshold distance. Now it should be lesser than or equal to threshold distance. Now if there are multiple such cities, our answer will be city with the greatest level. Okay. Now we are given some edges and that represent a graph and we are also given a distance threshold for. Now from a certain point, what we have to do, we have to find uh, to each node. From a certain point, we have to find the path to each other node, to other each other nodes, and that path distance should be lesser than equal to threshold distance. So this is what we have to do. So the first, uh, so first in the first criteria to solve this problem should know about Dijkstra's algorithm and how to implement Dijkstra's algorithm and how Dijkstra's algorithm work. So if you don't know how Dijkstra's algorithm works, you find out from some other video or learn how to implement it and then come to this video. It will be very helpful to understand this or to it will be very useful in this problem. So as you can see that this is our given graph and the neighboring city are distance threshold for each city at city 0 having 3 which is city 0 to have its distance less than equal to threshold to 1 which is 3 is less than 4 then 2 which is less than equal to 4 3 plus 1 is 4 less than equal to 4. So if it goes to any other city which is 4 so 4 5 6 7 greater than 4 so it won't be. Then from city 1 we have city 0, city 2 and certain all the cities. So as you can see the city 0 and city 2 have the minimum number of cities that are reachable through a through a distance threshold and city 3 is the maximum. So we have to consider this as our answer. So our given constraint are n is between 1 to 100 and our the next important constraint is our m is between 1 and n into n minus 1 divided by 2. Okay. So let's go toward this explanation. Now this is our given edges and this is the graph that we will form using these edges. So to form the graph, we will use list of list that will help us to iterate over the nodes easily. We won't use a matrix-based approach, we will use a list-based approach to create our graph. Then this is our given threshold. I have used three for a better explanation with some good examples. And this is our list of linked list graph that we are forming. So our 0 can go to 1 and 4. 0 can go to which and the 2 and 8 are represent their distance. Our 1 goes to 0, that 1 can go to 2 and 1 can go to 4 with that distances 2, 3 and 4. Now, this explanation won't give a much deeper implementation of Dijkstra's algorithm or explanation of Dijkstra's algorithm, but it will give a higher approach on how to solve this problem with the Dijkstra's algorithm or some methodology to do this. So you can also get a basic understanding of how to solve or how to use Dijkstra's algorithm in this problem. So let's take an example. So we will, in this case, we are using we are taking, for example, we are taking node 1. So we will use this node. So I will use this node to understand this problem. So in our priority queue, so Dijkstra's algorithm uses priority queue to find out the shortest distance from one node to another node. So in our priority queue, we will store one, which we are taking as our base node, and its distance is 0, as this will be our starting point of the node. And then we have a distance array, which will store all the distance from one node from our base node till other node. This will store the minimum distance. And then we have visitor array. This visitor array will check if we have any of the other node which is already visited. Now, first we will iterate over all the. So first we will what we'll do, we will iterate over all the one neighbors. So as you can see in this linked list, one neighbors it is 0, 2, and 4. So what we will do before storing into the priority queue, we will check if any of the distances are lesser than and equal to threshold value. So as you can see that 0 have a distance 2. So distance between 1 and 0 is 2. So is it lesser than and equal to 3? Yes, it is. So we will store it in our priority queue. We will also consider this distance that we are currently holding. So 0 plus 2 is less than equal to 3, so we will store. Then 3 plus 0 is less than equal to 3, we will store this, and 4. Uh, 4 has a distance of 2, this one. So is it 0 plus 2 is less than equal to 3, hence we will store it. So this will be our priority queue. So the path having the minimum distance will be at first. So we will use a lambda function for this. The next step, we will remove our top element from the priority queue, which will be 4 and 2, as 2 is the minimum frequency of any element. From all these elements, we have 0 and 2, but it's in the priority queue implementation, what it will store first. I have considered 4 comma 2. So our PQ first element we remove was P, 4 comma 2. And in our distance matrix, we will update at 4 position, we will update our 2, as this is the minimum distance from 0 to 4. From 1 to 4. And when visited, we are making our fourth index is true, indicating that we have already find out the minimum path between 1 and 4. And then we will iterate all the elements of the 4. So you can see currently we are holding weight as 2 and 4. So we will iterate over 0, comma 8. So as 8 plus 2 will become 10, which is greater than 3. So we won't store the priority queue. Now 2 plus 2, now it is visiting 1 again. So first we will check in which visitor key. So as you can see that in visitor 1 is already 2. So we won't do any further processing. Now now we reach at 3 here. So as you can see, the part distance between them is 1. So 2 plus 1, which is this 2 plus 1 is 3. So as 3 is lesser than or equal to 3, so hence we will store in our priority queue. So this will be our final priority queue. Then in the third step, we will remove 0, comma 2, as it will be at the top, as it contains the minimum distance. Now in the distance at 0, we will store 2, and in the visitor we will make it true. Now we will what we will do, we will iterate over all the 0 elements. So at 0, you can see that it has it has direction, or it has path between at 1 from 0 to 1. As 1 is already visited, we won't do any further processing. It has also a path till 4. As 4 is already visited, we won't do any further processing. And so So our priority queue remains the same. Now we have our 2 comma 3 at the top. We will remove it and check all its neighboring elements. So as you can see, the we have two our current holding weight is 3 because between 1 and 2 it is 3. So from 2 we will check. So at first 1 is already visited. So 1 is already visited. We won't go we don't won't do any further processing. Now we have 3. 3 is not visited and the currently 2 is holding weight as 3. So 3 plus 1 is 4, which is greater than 4. So sorry, which is greater than distance threshold, which is 3. So 3 plus 1 won't make 2 our priority queue. And so our priority queue still remains the same. Now we have our final step, which will in the first we will update our 3 to 3, 0, 1, 2, 3 to 3, and we will make our widget to true. Now we iterate over our three neighbors. So as 3 has 4, which is visited, already visited, and 2, which is already visited. Hence, we won't do any of the processing. And in our after, and now our priority to become empty, and we will remove out of our while loop. So, and then we, in the final step, we will find out the total number of reachable nodes or the reachable neighbors of one. So the total number of reachable neighbors of one till a certain distance threshold are 5. You can see the distance doesn't hold any max value. So 1, 2, 3, 4, 5. Okay. So node 1 has 5 reachable nodes. So in this case, node 1 has all reachable nodes. You can see this 2 is less than or equal to 3. Then 2 plus 1, 3. So 4 and 3 are also reachable. Then 0 is also reachable. So let's take an example of 0. As you can see, 0 between 0 and 1, it is 2, which is less than or equal to 3. So it is reachable, which makes it one reachable node. Then 2, so it is not reachable. As 2 plus 2 is 4, it is not reachable. Then it will iterate over 4 as 8 is not reachable. So for 0, there is only one reachable node with a certain threshold. So it is 1. So it has so 0 has a minimum. So we will consider this as an answer. So this will be the explanation for this problem. Let's go to our code. So I've initialized an ADJ. This will be for storing of our graph using a linked list method. Now it will store all the elements in a bidirectional fashion where I've implemented using int of array. The first we will store its neighbor, and in the second we will store its weight between one from one path to another path. Then we have an initializer result array which will store for each node, it will store the number of reachable nodes till a certain distance threshold. And now we will iterate over 1 till n for all the nodes. And this all root function will implement a Dirac algorithm and finds uh, finds the number of reachable nodes from that particular node to all nodes. So what will so this is as in this while loop is based on our example explanation, and this will be a priority queue. I use a lambda function here, which checks between uh, each frequency or which checks between each weight. The lesser the weight, it will be at our top position. This lambda function does that. Now we have reachable node initialized. Okay, now let's also explain this. Okay, I will also explain this while loop. Until our priority queue won't get empty, we won't get out of this loop. Now we are uh, popping out our first element and making its distance at node distance. And this will be our node distance. And we are making each visited node to true. Then we will iterate all its neighboring uh, element as stored in our linked list. And we are checking if we have already visited its neighbor node, and then we are checking using this condition if node distance plus its current distance is less than or equal to our threshold distance. And if both of these conditions satisfy, we are adding it in our priority queue. Now, the last step, what we will do is we will check for all distance. If any of our distance is max value, then we a reachable node won't get incremented, and at the end we will return our reachable nodes. Now, this for loop is to check for our answer which reachable node has the minimum value, and to update and to get, and we will get this node using this I, and at the end we return this node. So the time complexity of this approach is, so first we are iterating over n, so big of n, then we are iterating over m, so big of n plus big of m, then we are iterating over till n from I equal to 0 to n, and this all would take time complexity as, so this while loop take time complexity is big of uh, till it takes e is our all our edges as we are as we so e is our edges, so e are all our edges, so e is all our edges in our graph, so it is going all through all our edges through some vertices, so it will be big of e plus v log v. So v is our all, v are all our nodes, and log v because in priority queue insert and remove element in big of log n time or big of log v time. So time complexity for this whole for loop and this form and this function will be big of v. So consider this as a vertices is, so v mm, into v into e log v. So the time complexity of this up will be big of v, as v will be a vertices into e plus v log v. So this will be our time complexity, and this is our big of v. So our maximum time complexity is this one, which is v into e plus v log v, and our space complexity is big of v, because we are using a priority queue to, and this priority queue will store all the vertices of our graph. So okay, so this will be it for this problem. So I hope you understood the problems and explanation, and did give a little understanding of what type of data structure or what type of approach we should use in this certain kinds of problems. So this will be it for the videos. I hope you understood. Thank you. Goodbye.